Hello everybody. Welcome to a new video. Today we're going to solve the binary tree Inorder Traversal on LeetCode. So we have here a binary tree and we need to return its Inorder Traversal of its nodes. So let's take this example to have a better understanding. Here we have a tree with 1, 2, 3 and the Inorder Traversal is 1, 3 and 2. Why? Because first we have our root, then we check its left. It has no left, so we can't put actually one. That's why it's here, okay? Then we're going to the right. But before putting the right node, we need to check the left of this right node. The left of the right node, again, before putting it, we need to check if it has no left. It has no left, so we can't put it. Then we're going to check its right. It has no right, so we can go back to this node. So this node, we can put it, and it has no right, so we can stop here. That's what we have here. And root of an empty, so if you have a tree, an empty tree, just return an empty array, no problem. If we have one element, we just add that specific element to our result array. Let's take this example and try to do the Inorder Traversal. First of all, okay, I'm at the root 1. But I cannot put it directly. I need to check its left. Okay, can I put 2? No, because it still has a left. Okay, so now I'm going to check the 4. 4 has no left, so I can put it. Then I can go back to 2 and put it, and then check again the right. Okay, the right had no left, so I can put it directly. Cool. Then I can go back to 1. So I finished its left side, so I can put it here. And then put the right. Well, actually, because I didn't have any left here, so I can put it directly here. Cool. Now, how are we going to solve this problem? Actually, we have two approaches. A recursive approach and an iterative approach. First, let us see the recursive approach. In order to traverse all this tree, I need to divide it into sub-problems, okay? So first of all, I need to traverse this tree. So I need to traverse the left sub-tree of my root, okay? And in order to traverse this tree, I need to traverse this left subtree, and so on. And after I finish traversing, for example, after I finish traversing this subtree, okay, I can add the root, quote unquote. It could be a local root, not a global root. So the root of the subtree. I can now add it to the result, and then I can go and traverse recursively the right side subtree. Okay, so let's see how are we going to translate that into code. First of all, I need to create a variable called it's going to be an array list of integers called results. Then I need to return the results at the end, basically. But before, I would need an intermediate a helper function, okay, that we're going to call helper, and it's going to take as input a root and also an array list of that is a result, so we can keep track of our results while going through the recursive function. Nice. Then we're going to check first of all if the root is null, because if the root is null, we just need to restop our recursion. And if it's not null, we need to traverse the left side of my tree. That's why I need to put here root left, and here I need to add my result, basically. And then if I finished going through the left side, the left subtree of my tree, it just add now the value of my root. And then after that, I can traverse the right side of my tree. Okay, so here result. Cool. And then I can call my helper function here, helper with root and result. Now let's see if it works. Hopefully it works. Okay, it works. Let's submit it. Yes, it works. So the time complexity of this algorithm, well, first we will need the time complexity equation. And to do that, first of all, we have t of n, and here we have two recursive calls. So the first one, as you can see here, instead of we go to the left subtree, so we're going to half of the elements that we're supposed to go through. Okay, that's why here we're gonna put tn and divided by 2. So at first we had n elements, okay, but then we choose to go through the left side. So here we're just gonna have half of the elements to go through, okay, and then we need to add O of 1, because adding a value to our array is O of 1, and then I'm gonna need another tn divided by 2 for the other one. Okay, so the time of my recursive, the global time of my recursive function is equal to the time needed for this recursive call plus the time needed for this recursive call. And the time needed for this recursive call is tn divided by 2, and tn divided by 2. To simplify, it's 2 tn divided by 2 plus O of 1. There is a theorem called the Master Theorem. I will let you have a look at it. So the Master Theorem, and it can help us to get directly the solution for this recursive relation. And for our case, the solution would be t of n equals to O of n. So actually our recursive approach is linear. So this is the time complexity, but for the space complexity it's going to be O of n2. Why O of n2? Because in the worst case scenario, imagine that we have only elements that are like this, that just have left. So we need to go to this left subtree, then go to the left subtree, but before calculating this we need to calculate this and this and this and this and so on. That's why we need here, like in the worst case scenario, it would be like the number of elements on the tree. That's why here we need on space. Cool, but now let's try a new approach. I'm gonna just write down a new tree. 1, 2, 3, 4, 5. Now let's try the iterative approach. In order to do the iterative approach, we will need a stack, a big stack like this, okay? And we will have a pointer called current. This pointer will point to the root, so at first, okay? Then we will have a loop. We're going to loop through all the elements of the nodes, obviously, and we need to we stop when the current is null, and also the stack is null. For our case, the current is not null, so we cannot stop our loop, okay? But in the case that we had, like for example, an empty tree, current would be null, and the stack is null too, so we're gonna stop just directly after that, okay? Okay, cool. So the first thing we're going to do is we're going to check if the current is null. So our current is not null, so we're gonna add it to our stack. Okay, then we're going to replace our current with a new element, that is 2. So we put the left of the element that we just put in the stack in the current. Okay, cool. Then we check again if the current is null. No, the current is not null. So we're going to put it again in the stack. We remove it. Then we put the right of 2, that is 4. Again, we check 4. 4 is not null, so we're going to put it in the stack. We remove it, and then we put its left. Okay, but this time it's null. So if this time it's null, what we do is we're going to pop the element from the stack and actually put it into our result. Okay, and then, okay, so we've done that. Then we're gonna do it again. We're gonna come here. The value of current is still null. So we're gonna pop again the element on the top of the stack and we're gonna put it into our result. But this time we're gonna put the right of 2 here. Cool. Now when we come back to 5, 5 is not null. So we're gonna remove it and put it into our stack and put here the left of 5, that is null. Oh, we have a null here this time. So we pop the element on the top of the stack and we put it here. And then we put the left of 5, the right this time, we're gonna put the right of 5 into the current. But it's still null. So we're gonna pop again my stack and put it in my result array. And then I'm gonna put the right of 1 into my current, that is 3. 3 is not null, so I'm gonna put again 3 in my stack. Cool. And of course put in the left of 3 here, but that is null. I come back again, the next iteration, we have a null in our current, so we need to pop the top element of my stack and put that value into 3. And then put the right of 3 here, that is again null. As you can see now we have a null here and we have an empty stack. That means that we should stop our program. And here it is. Now we have our correct answer. I'm just going to compare it with here. 4, 2, 5, 5, 1, and 3. That's correct. Nice. Let's try to code it. Cool. Let's go. So first of all, we would need an array list that will hold our result. New array list with the result. We'll also need a stack of integers called stack new stack. We will also need so this, it won't be of integers, but it would be of 3 node, because we need to keep track of the right and lefts of the nodes. So we need to keep the 3 node, not just its values. And then we're going to need a current that will. Hello, I'm back. The video got cut off because I had no more space in my disk. That's a bit unfortunate, but let's continue. Okay, so here we've initialized our current to root. Then we will need our loop. To be still in the loop, the current must not be null, and also the stack or the stack must not be null. Okay, so we're gonna add that. The current must not be null, or the stack is not null. Cool. Okay, then we're gonna do our first check if current is different from null. What we need to do, we need to push that current to the stack to save it later and put into our current the current left. And if the current is null, so we have arrived to the end, that means that now we need to pop the top element of our stack and add that to our result. and add, you know, the current dot value to our result. And then we can go now and check the right side, the right subtree. Okay, and then we return the result. And yeah, everything looks good to me. We run the code. Stack pop cannot be applied to given types. Whoops, I don't need to add that. Whoops, we've made a mistake. Not left, right. Run code. Okay, finally it works. Submit the code. It works. So that's it. The time complexity is O of n2 and space complexity is O of n, because at the worst case scenario, the stack will hold all the nodes values for the same case here. Like this, if you have this case here, the stack will hold all the nodes elements until the end. So we have O of n time complexity and O of n space complexity. Thank you for watching. See you in the next video. Bye.